All right. Well, thank you very much, everyone, for having me here today at Data Minutes. I love lightning talks, and an event full of lightning talks, I'm very happy. So thanks for putting this wonderful event on and for having me here. We're here to talk about something kind of near and dear to my heart, Columnstore indexes, specifically compression and how does it work. To many people, it's a black box. You put a Columnstore index on a table, it gets smaller and faster, and everyone's happy. But the details matter and can make your life a lot better. So this really is what makes analytic data performant in SQL Server. Quickly, this is me. I publish multiple books now. I have a Columnstore index book coming out in about a month. I have chapters and articles. I have a senior data architect at Datto, a company that provides all sorts of SaaS tools out. We're centered in Norwalk, Connecticut, Albany, New York. We have offices all over the place. Not that offices matter much anymore, but I also organize SQL Saturday Albany, a great event out here. Took a year off last year, hoping to run a big event this year. More on that, hopefully, in the coming months. So I love doing this. This is a lot of fun to me. I find data enjoyable to work with. I get laughs out of this. I meet great people at these kinds of events. So this is wonderful. Let's jump right into it now. You have 10 minutes, right? That's how this works. So what are we going to do? Quickly review how do Columnstore indexes store their data. We'll talk about the 3 basic steps in Columnstore compression. We'll say why this is important. And in the last few seconds we have, you can think about questions and then send them over to me on Twitter or however else we're going to handle questions here, because there sure as heck ain't time for them now. Most important piece here to understand Columnstore compression is how is data stored. In a Columnstore index, rows get grouped into what are called row groups. A row group is up to 2 to the 20th rows. We'll call it a million for argument's sake. And you could have as many row groups as you need. And within each of these row groups, these bundles of rows, each column is individually compressed into what's called a segment. A segment is just all the values in that row group for that column compressed together. And as a side note, this is all for analytic data only, OLAP style data. All your transactional kind of data, OLTP, does not belong here at all. But because that data is stored column by column, it compresses very, very well. And a lot of what happens here becomes far better than when you talk about standard compression, row compression, page compression, backup compression, zip compression, and other common algorithms become very, very effective when you have common values, data types, and repeatedness. So step 1 in Columnstore compression is to encode your data. The purpose of encoding is to take your data and represent it in a way that takes up less space in any way possible. There are many types used. The most common ones used in Columnstore compression are dictionary encoding and value encoding, the first of which I will demo shortly. These algorithms don't incur any loss, neither do any of the Columnstore algorithms. The real purpose is just to reduce data footprint and prepare it for further compression down the line. I put a few DMVs here. I'll post this deck up later so you have it. They provide information all about how encoding works in a Columnstore index. They tell you exactly what are in the dictionaries, how is each segment compressed, and what are the details for how it is compressed. So you want that information. It is sitting there in system views waiting for you to look at it, which is very useful. Here's a dictionary encoding example. Here's one way to take a list of delicious data here and make it take up less space. So this tasty list of information here has 203 bytes worth of values and 11 values. A real analytic table could have millions, billions of values. We got 11 here because my screen is only so big and my eyesight is my eyesight. Yummy. Great. First step to making a dictionary encoded segment is to take your values and turn it into a lookup dictionary. So your dictionary will have one for each value, one row for each value, and a small index ID. Our original values took up 203 bytes because 1 byte per character. If it was nvarchar instead of single byte, it would be 406 bytes, double width characters. Your lookup table here now has a little index ID, one of each value, and that size. So our dictionary is 82 bytes. Great. Final step is to take our data set, take our dictionary, and cross them. And in doing so, our data set now becomes a set of index IDs. And so instead of being these big, long strings take up a lot of space, now it is these teeny little numbers. And note that I put the size as 3 bits. When you Columnstore compress data, it doesn't do it in ints or small ints or big ints. It uses as little space as possible to store its data. So if an integer takes up only 3 bits, it's stored in 3 bits. Awesome. So our dictionary encoded data isn't even in bytes here. We're talking 33 bits or like, what, 5 bytes? So we've taken 203 bytes of data and turned that into about 85 bytes. So we shrunk it down to about 40% of what it was originally. This is dictionary encoding. It is used very frequently in column store compression, and it can be combined with other types of encoding and compression to get further space savings. So this is example one of one way to encode data. A value encoding, the one I mentioned, is a little more complicated. It involves taking numbers and using division or negative exponents in order to shrink down the size of the number to some common denominator or exponent. In doing so, you make each value shorter and take up less space. So it takes up 8 bits instead of 3 bits, 8 bits instead of maybe 20 bits, or a byte instead of 2 bytes, so on and so forth. The next step after you have encoded your data and made it smaller in that fashion, note it's not really been compressed yet, it's only been encoded. There's still values in a big long list. The number of values is equal to the original set of values. Optimization is a very important step. Because the row order within each row group does not matter in a column store index, there are no clustered row store indexes here or rearranging your rows for you. You can rearrange the rows within each row group however you want, and that's called optimization. In SQL Server, it's called VertiPaq optimization, and this is a huge, huge way of saving additional space because it will reorder the rows in a way that makes them compress better. One note on this is it is expensive, whereas encoding is kind of cheap to do resource-wise. Optimization is expensive. Rearranging rows and figuring out the best order is not come cheap. But what it will do, it will not save any space in of itself, but it will set up your values and your segments so that the next step, compression, you can compress the data far better. A really simple example of what optimization means is here's our encoded data from step 1, a bunch of values 0 to 4. What optimization will do in this case is say, I'm going to order them by value. So instead of it being 0, 1, 2, 3, 4, 2, 2, 4, whatever, it's going to be all the zeros, all the ones, all the twos, all the threes, all the fours. So like values will sort together. Again, the total size in bits is the same. I've not saved any space here, but in the next step, you'll see why this helps us a lot. The last step in column store compression is to actually compress the data using what really comes down to more traditional compression techniques, the stuff that you're more used to when you think of compression. Microsoft uses the X-velocity algorithm in Columnstore and the Express algorithm in Columnstore archive. If you're interested in those, you can Google them. I don't have time here to talk about them, but they're interesting. Some information is public, some is not, but you can learn about how they do what they do. The real focus of all of this, though, how this compression works, is taking repeating values or byte patterns and squishing them together to take up less space. And because of that, the optimization step in step 2 is key to making this happen. So here's an example of what's called run length compression. It takes multiple values that occur sequentially that are the same and groups them together. So here we have 0, 0, 0. We can really just say that's the value 0 and it occurred 3 times. 1 occurred once, 2 occurred 4 times, 3 occurred once, 4 occurred 2 times. And this is an algorithm that is great for sorted data. That is, optimized data, and it's not too expensive to do. Another kind of compression is bit array compression. This is more expensive, but it is really good for unsorted data. So if all else failed and I couldn't encode or optimize my data and my data is exactly the same as it was earlier, I could create this little like hash table of ones and zeros that would basically say, here's all of my possible values, put a 1 wherever the value is, and we're done. It takes more effort to do this, but it does compress pretty well as ones and zeros do not take up a lot of space. But this does consume more space than the previous example by a little bit. We can take this information and use to tweak compression and make it better. For example, SQL Server cannot use VertiPaq optimization for new data inserted into a column store index, a clustered one that has non-clustered row store indexes. If you have those and you need them, you've got to work around them through either rebuilds, drop, rebuild the index, re-add, or other tricks and tips. I have articles about this out there, by the way, that will tell you all how to do this if you're interested. In addition, memory optimized column store does not support optimization. It may not matter to you, but it's worth just knowing that's the case. In case you're wondering, why is my memory optimized column store index so big? This might be the answer. One final note is that dictionaries used in dictionary compression are limited to 16 megs. This is a big deal. If you have very long values, very wide values in your columns, you may find dictionaries will hit the limit. They'll then split your row groups into smaller row groups. And if you know about column store indexes, you know that undersized row groups waste space. They don't compress as well. They waste space. You get more row groups. And in general, things don't perform as well. So what this means is if you have wide columns, try to normalize them. That will probably improve compression as we'll take those big wide values and move them over here. On the other hand, very, very teeny narrow values, you can normalize if you want, but it may just waste resources in the long run, the resources of doing all that effort. So to wrap up, compressing by column means you can compress data amazingly well, better than most common scenarios for compression in the real world. That's why Columnstore indexes compress your data so effectively. As a bonus, that data doesn't just stay compressed on disk, it gets compressed in memory, so your I/O is better too. So the smaller your data is, the better you can get it to compress, the smaller it'll be in memory, and you're saving all kinds of computing resources now, and because of that, making your indexes and your analytic data queries faster. All that tweaking I mentioned will help you make your data smaller and faster and better. And last but not least, all those wonderful dynamic management views out there provided by Microsoft give you complete transparency into how these things work and how they store their data. So if you want to know how they work, feel free to take a look at those dynamic management views. They're easy to find on Microsoft's documentation or in articles I've written or other people have written. So use that to learn more about your indexes and make them as fast as possible. And with that, that was 10 solid minutes of talking at 1.5x. So I think I am done now. If you have any questions, feel free to send them over to me on Twitter or email them to me or however you feel like getting them over to me, and I will certainly reply. So thank you very much again for having me here. I really appreciate it and hope you enjoyed this.